So now we get to a really funky linear transformation. We're taking a linear transformation from the set of polynomials at most degree 2 to the set of polynomials at most degree 1. And our linear transformation is the derivative of the polynomial plus the integral, the definite integral of the polynomial from 0 to 1. And for those of you who haven't taken integration yet, I'm going to spoil this surprise for what this integral is. But first, what we're going to do is we're just going to show that it is a linear transformation. And then after we show it's a linear transformation, we have to show that it transforms W1 to W2. To prove it's a linear transformation, the left side is going to be T of A f of x plus B g of x. And here we're going to let f and g be in P2, P2 defined over the reals, and A and B be a real number. Our left side is T of A f plus gx, and our right side is going to be A T f of x plus B T g of x. And our right-hand side is going to equal the derivative with respect to x of A f of x plus B g of x, which plus the integral from 0 to 1 of A f of x plus B g of x. And we're going to distribute our integration and derivative operators over these operations, giving us A d by dx of f of x plus B d by dx of g of x plus the A times the integral from 0 to 1 of f of x with respect to x plus B times the integral of 0 to 1 g of x dx. And the right-hand side is going to be equal to A d by dx f of x plus B plus the integral from 0 to 1 of f of x dx plus B d by dx of g of x plus the integral from 0 to 1 of g of x, or plus B times the integral from 0 to 1 g of x with respect to x. And rearranging, we get A d by dx f of x plus the integral from plus B d by dx g of x plus the integral from 0 to 1 f of x dx plus the integral from 0 to 1 g of x dx. And now we have shown that the left side equals the right side. Therefore, T is a linear transformation. And I had mentioned that we were going to show that T does map V to W, but we're going to take that as an assumption. If you want to verify that for yourself, you can go through that proof. But the idea is that this function takes polynomials of degree at most 2 and outputs polynomials of degree at most 1, whereas this function outputs constant values. So we're going to have some constant plus a polynomial of degree 1, giving us a polynomial of degree at most 1. So now we have a linear transformation, and this thing is weird. And we want to find the null space and the image of this thing, and it's just weird and it's ugly, and we rely completely on our setup. But our process isn't going to change at all. We start by solving for T of beta alpha, and we want to know what happens to 1, what happens to x, and what happens to x squared. And what happens to 1? Well, the derivative of 1 with respect to x plus the integral of 0 to 1 of 1 dx is equal to 0 plus the integral from 0 to 1 of 1 dx, which equals x evaluated from 0 to 1, which gives me 1 minus 0, which equals 1. Now, 1 is equal to 1 times 1 plus 0 times x. And now I've got my coordinates. T of 1 represented in beta is going to be 1, 0. Now, if I look at what the derivative of x is with respect to x, plus the integral from 0 to 1 of x dx, this is going to equal 1 plus the integral from 0 to 1 of x dx, which equals 1 plus x squared over 2 evaluated from 0 to 1, which equals 1 plus 1/2 minus 0, which equals 3 over 2, which is equal to 3 over 2 times 1 plus 0 times x, which tells me that the coordinates of t of x in beta is equal to 3 over, well, let's scroll up. Let's scroll over. 3 over 2, 0. And now if we look at what happens to t of x squared, we get the derivative of x squared with respect to x plus the integral from 0 to 1 of x squared dx, which here, this is going to be 2x plus the integral from 0 to 1 of x squared dx, which equals 2x plus x cubed over 3 evaluated from 0 to 1. Now, in terms of calculating these derivatives and calculating these integrals, this is not something I'd expect you to know how to do. In fact, if I were to ask you to do this on an exam, I'd give you what these expressions were. I'd give you what these derivatives were. But for this example, I'm just doing it for you. And it shows you that more complicated things can happen. Well, this is going to equal 2x plus 1/3, which equals 1 over 3 times 1 plus 2 times x. So the coordinates for t of x squared represented using beta is going to be 1/3, 2. And now from here, we can compute what t of beta or alpha beta is. And it's equal to the matrix 1, 0, 2/3, 0, 1/3, 2.